Thank you all for joining. This is the Markforged Metal X webinar. My name is Marcus Brown. I've been with MLC CAD for about 12 years. I'm a mechanical engineer in our Stillwater, Oklahoma office. And I love the Metal X. I love talking about it. So today we're going to cover three main topics related to the Markforged Metal X printer. So we're going to talk about how exactly you print metal. It's kind of crazy, right? There's a lot of different processes out there. A lot of times people get them confused which one does what. So we'll cover really quickly what they are and how this particular process works. We'll cover some common questions that we get from people about the process, wanting to know, why certain things are the way they are and if there's any change that we can do if they don't like it. There's also some ROI discussion we're going to have, not because I want you to go through the ROI and I want to push you to buy it, but because the ROI is a little bit weird on this. Not because necessarily it follows different rules, but because it fits into your business in a unique way. So a lot of people have built their business in a way that sort of circumvents these problems and you just sort of don't recognize them as being in the background. But we can talk about where to find an ROI and what kinds of companies can actually expect to get an ROI for something like this. So we'll start with just metal additive manufacturing in general. There's a couple different methods for manufacturing metal. We start out with just metal printing directly. And that usually involves either some kind of a big laser or a welder or something where you take a rod or you take powder and you put it on the part and you let it cool down. Now the problem is that tends to be extremely expensive. A lot of these machines you can't get in the door for less than $1 million all in for the machine, the materials, the safety, the facility requirements, and any additional machines that must be used. There's a lot of safety hazards involved with loose metal powders and with lasers, and the parts are actually fused to the print bed, so you're going to have to cut them off the bed and clean them up, which involves a lot of metal cutting. And because they're printed almost as an entirely weld part, you want to kind of keep your stress concentrations away from the weld areas. These parts are all weld areas. So you see bubbles and other problems and defects caused by, and Z-axis effects caused by the manufacturing process. Now, another approach to printing metal is to not print metal, but to print the things that make metal. So we see a lot of people talk about this. They say, well, why don't you just make that as a sand casting? And the answer is, well, if you've got access to sand casting, go for it. In fact, that's a fantastic manufacturing process, right? You're going to build your cores. You can even 3D print wax or 3D print the core shapes and build your sand using those additive components. But it requires access to a foundry. It requires that you use materials suitable for casting. And there are strength restrictions and strength accommodations that you've got to make when you're doing some kind of casting. So it's not for everybody, but it is definitely possible to do. But what we're going to talk about with the Metal X is atomic diffusion additive manufacturing, also known as ADAM. Now that I've explained the word and the terminology, forget that that's what it's called because it doesn't matter. It's a three-step process where you have metal particles, a metal powder that's bound together into a material. You print it like a traditional 3D printer would. You debind it, and then you sinter it to solidify it. It's much more office friendly, it's safer, it's a lower cost, and the infrastructure costs are way, way lower. And so this is what we're going to go through, is explaining how this works in general and specifically for the Metal X. So it starts in the software. The software is called Eiger. You don't need to know that the software is called Eiger, but if I ever say the word Eiger, I'm just saying in the software that comes with the program, you upload your file and tell it what you want to do with it. And this is the same interface for the composite parts as it is for the metal parts. So you specify what kind of material you want it to be made out of. It'll check to make sure it's going to be usable in that material and fit in that machine. Specify the layer height you want to use. For Metal X, right now we're looking at 2/1000ths or 5/1000ths of an inch. That kind of determines not only the detail level that you can achieve, but also kind of controls how fast you're going to be able to print. Larger layer heights mean you'll print a little faster. Look at the support structure. For parts like this one that have some overhangs, you will have to build up something to kind of support the part during the sintering and printing processes. And you have an option to add a raft or not. And you can specify sparse fill, which means kind of hollow interior space to reduce the weight and reduce the amount of material used. And you can then specify how thick you want the walls and the floors to be to create a solid, strong part where it's solid on the outside, but then has almost like a bone structure, a kind of an organic sparse fill interior. All the information that you specify affects how much it's going to cost, the weight, the print time, the wash time, and everything else, and all of that is being displayed in real time as you make your changes. So let's say I wanted to save some time and some cost. I could make the print height, the layer height a little bigger and turn off the raft and see what impact that's going to have on my bottom line. From here, you can take a look at the internal details of the part. So internally, the part is going to be split into individual layers, and it's going to build up not only the raft and the supports, but the part and any ceramic release that we'll talk about here in a second. And you can tweak and make sure everything looks exactly the way you want it before you commit to it. So you have full visibility into what the plan is and also the exact tool paths, basically, the print head paths that are going to be used prior to committing it to making one out on the machine. So you get this all done, you put it in there, you say, this is how I want it to be built. Let's print some. Right? And this is super simple. You just basically drag some parts out on the table and move them around. I threw a bunch of them on here just to see how many I could fit. And this takes about a week to print. So if you got a week's vacation coming up, you could print a whole bunch of them. If you're just trying to get one out, you can just print one of them at a time and then take it, run it through the process and test it, and then repeat. So there's not like a benefit or a penalty for going one at a time or doing a bunch at a time. And this is a very unattended operation. If you say, I want to print all of these, it'll just kick off, and for a week, it'll just print away until it maybe runs out of material. Then it'll pause and send you a polite email telling you, hey, fill me back up so I can continue this print along the way. So the whole process is really simple. Inside the interface, you also see the machines that are available. So you can see what the status of each of those machines is, as well as if there's a queue involved, so you can kind of see what the length of the queue is. So if you're in a hurry to get a part printed, you can get a realistic expectation of how long it'll take by seeing what kind of line people have created to try to get into that machine. Also, you can see the individual print jobs, and then wash and sinter is also shown, so you can kind of track your parts all the way through the process very easily, very clearly inside this Eiger interface. So as far as managing the workflow, you're not going to need, a bunch of job travelers and a bunch of people moving parts and moving things around. You'll need people to move parts, but generally speaking, all the tracking is done here inside the software. And that does roll up into reports and other information about what parts you're printing, how much utilization you have on those machines, who's doing it, what's the most popular material being used, and all that information can allow you to really understand and track this resource utilization within your company. So I mentioned it's a three-part process, and it's all controlled by software. This is basically what's happening along the way. You start out with your CAD design, whether it's an STL file, SOLIDWORKS file, whatever, and you put that into the Eiger software. Tell it what you want to do with it, and it then will send it to the printer and print it as what's called a green part. That green part then needs to be washed, where it's then technically considered a brown part, and then after it's washed, it's sintered in an oven, and after that, it's just a part. It's a metal part. You're done. You don't have any cutting or any other post-processing required unless you want to. So let's go into detail of what is actually happening in those three steps. I want to kind of take away any mystery or magic here, because this information, or the process itself, I think is not only really fascinating, but it is also very telling about what you're getting and what kind of compromises you will or will not have to make along the way. So the printer itself looks a lot like a regular FDM or kind of extrusion head printer. In fact, Markforged started out printing out composites with continuous carbon fiber. Those all came off of spools and extruded through a print head, and they're utilizing their expertise in those areas to be able to print metal parts the same way. There's two spools. There's a metal spool and a ceramic spool. We'll talk about what that looks like. There's the picture of the build plate. When it's printed, you'll see that everything that was set up inside Eiger is actually printed out in the real world. So you've got the metal part as well as the metal raft and supports. And then that white line, see that white line in there? That's that ceramic release layer. When you center metal, it creates solid, strong, durable metal parts. When you center ceramic, you create a ceramic part that is brittle. And that's how you release the part and any supports from the rest of the part without any cutting required. You'll see there's two nozzles in the machine there. This whole area is all heated. So the chamber is heated, the bed is heated. The material itself is a little bit like clay in that you want to kind of warm it up a little bit to get it to flow a little bit. Instead of sort of getting it wet, you're getting it warm. That makes it flow. A lot of the time you see problems with people on a fused deposition modeling printer have problems with bed adhesion and also with removal of the part. You want the part as it's printed to the bed, you want it to stick really well. And then when you want to take it off, you've kind of got to pry it off with a spatula. And so we use this vacuum table with wax paper. And so you just set it down and it sucks the paper down. That wax paper in the heated environment is the ideal substrate for this printer. You get a fantastic adhesion, and then when you're done, the vacuum is disconnected and you can just peel it off, almost like the back of a sticker, peeling it off of a sticker, and the part is now ready to use, and the machine and the bed and everything's very, very clean inside. So you don't have a lot of mess at all with this type of a machine. The material that's being printed is a three-part mixture. It's about 80% metal, and it's bound together with wax and polymer. Now, each of those serves a very specific purpose. The wax, along with the temperature that the extruder puts that material at, creates this very good spreadable material that doesn't clump and doesn't skip and break. I mean, if you've ever tried to spread either really cold or really hot peanut butter, you know that getting it the right temperature, the right consistency gives you an absolutely perfect result, and it's a lot easier to work with. The wax and the polymer hold that all together, and by warming it up, you get the perfect consistency to lay it down. Now, the final result we want is only going to be metal. So we start taking these things away. The first thing we do is take away the wax in the debind, the wash station. So the wash machine, the Wash 1 is the name of the machine, is a solvent bath. It has a vapor reclamation system. So it's, as the vapor comes up, it gets reclaimed by some cool coils. And so it doesn't smell like, unless you stick your head in the top of the machine, doesn't smell like there's solvent there at all. Really pretty amazing. And the parts, you just stick them in the basket, drop them in the solvent bath, and it attacks and pulls away the wax, leaving the polymer and the metal completely untouched. You could leave it in there for a month if you wanted to, but you only need to leave it in there for as many hours as is specified by Eiger. Once it's done and you've got it, all the wax removed, you throw it over to the drying chamber, dry it off a little bit, and you're ready to sinter the part. Pretty simple and easy. The finished part after the debind is no wax, and it's a part, again, it's a little bit like clay, like a dried clay at this point where it's not fired, but it is holding together really well. And the wax is all gone, and the metal powder is not bound together, but it is held together by that polymer. Now this creates a unique step. This is something that you don't see with any other manufacturing process with respect to metal, is you now have your part in hand and it's not yet solid, which means you can do special things like green sanding. Green sanding just means that if you were to take this part, use a little wet sand and sand it down, you would be able to aggressively remove material, very much like, again, a dried clay part, but it's metal. By using wet sanding, you're capturing all the metal particles, so there's no health hazard and safety hazard, and you can kind of clean up the surface finish very quickly and easily. Again, it's a little bit like wet concrete, right? Go in there and carve your initials in it if you wanted to, and then you could go center it, and it's boom, it's solid, ready to roll. So for certain operations, that's a really unique and interesting opportunity to do some things with that part if you need to. If you don't need to do that, once it comes out of the wash, you're ready to go into the oven, the center oven. This is the center 1. There's also a center 2. The center 1's kind of like a tube, an oven tube, and it gets extremely hot in there. The center plate is where you'll arrange all your parts. If you've got larger parts than what will fit in the center 1, you'll want to go with the center 2, or if you've got a lot of volume, you can go with the center 2. Center 1, the volume is about the shape and size of a loaf of bread. And those parts get put in there. That touch screen kind of guides you through the process of preparing the gas, preparing the build plate, inserting the build plate in, locking the door, putting in the heat shield. All that computer-controlled information is very helpful to help you get this thing going. And once you fire it up, the process will start to outgas and burn off the polymer, turn that into vapor, and it'll be vented. But the metal will start to melt. Now, this is the part that blew my mind, right? This is the part that I said, well, hold on a minute. You're melting it, and it doesn't just turn into a puddle. Sintering allows, it's just below the melting temperature. It allows the metal crystalline structure to merge with its neighbor and slowly grow the crystal boundaries, and they slowly start to merge together over time. It takes about 24 hours to heat, hold, and then cool the parts to where you can work with them. But the polymer, the gaps in there held together by the polymer, that is where the gases escape, is through the holes that the polymers were holding together. And at the end, you're left with a 99% plus dense part made of metal with no residual effects or even memory of where it came from or how it got there. The only thing that will indicate that it used to be a bunch of metal powder is that you'll see the layer lines from the printer process out on the perimeter, and there's a sparse fill inside. Otherwise, it's a solid metal part like any other. You'll take those finished parts out of the oven, and it'll start out looking like this part down at the bottom right of my screen here, where the part and the raft are connected, but there is a separation layer with that ceramic. So what you do is you take that part and the support, and to remove the support, you basically just twist it or you drop it on the floor. Drop it on the floor is actually the easiest way to do it. And the part just kind of shatters that ceramic, that tiny ceramic layer. You get a little bit of ceramic dust, and you now have a perfectly finished part with everything removed, all the supports and rafts removed, and then you recycle the support and the raft. Now, you can do without the raft if you want. When it shrinks, it does kind of slide a little bit along that surface of that plate, so the raft kind of insulates your part from that deformation. So a raft definitely gives you the most accurate and precise part possible, but if you want to save material, it's definitely possible to just print it directly and run with it. In fact, there's some really cool design ideas for how to kind of minimize that effect, but these parts are ready to roll. They're solid metal parts with no additional processing needed. Really pretty amazing. So that's kind of the total process, start to finish, right? Build the part you want. Eiger will upscale that part to print it, and it'll print the part. You can then wash it in any time you want. There's no like time restraints on wash. You don't have to hurry up and do it or anything like that. Wash it and then center it, and you get full metal parts coming out the other end that are ready to use right away. So if it sounds too good to be true, you're not alone. A lot of people have a hard time with this process. It's a really powerful process, and in fact, it's not a new process. Sintering and 3D printing are not new, but it's a new application. It's a new way to do it. So let's kind of talk about some of the commonly asked questions and some of the misunderstandings we get a lot of times with this. A lot of these questions are coming from our YouTube channel. So we built a video called, the Markforged Metal X is here. I'll put a link in the comments at the end of the webinar. And we had 100,000 people view that video and put in all kinds of comments. And they were very eye-opening for us because there were things that we did not do a great job of explaining, or that just simply weren't as intuitive for somebody coming in from the outside. So we're going to use that to kind of guide our commonly asked questions. I think the reason there were so many questions is that this process is very unfamiliar to a lot of people. Not a lot of people are aware or exposed to the sintering process. A lot of times people aren't even really familiar with additive manufacturing, or if they are, they think of it more as, printing toys or printing conceptual, prototypes for like trade shows, not for printing parts that are going to be full production, full strength parts. Sintering seems like a bit magical, so we'll talk a little bit more detail about what goes on in the oven during the sintering process and what that has, impact that has on your finished parts. But a lot of times people just simply think it's either too simple or too complex. It's kind of interesting, from comment to comment, people will say, wow, that's awesome, that's really cool, or no, that's way too many steps, right? So we're here to kind of help with that skepticism, that healthy skepticism, and build some trust. So you can see that this is not magic, this is not futures, this is a great machine that may be a really fantastic situation for your company. The first thing a lot of people freak out about is the cloud. And understandably, there's other scenarios where people have implemented the cloud in certain ways that have not been ideal. Let's talk about some of I kind of categorized all the questions and comments. One of the big ones is, hey man, cloud is unreliable, or my internet is unreliable, or any problems with the internet access is going to ruin my print, and I can't deal with the security nightmare that involves uploading my files onto a web server. Well, the cloud, it just hosts the software and does the slicing and the storage. That's it. Right? I bank online, I put my Dropbox files online, I put a bunch of stuff online currently. The only thing that happens is that transfer and that processing. The rest of it is completely offline. So the machines run offline, and you can transfer files with a USB drive if you want to offline. You can completely not use the tracking inside Eiger. And if you don't want to go online at all because of security issues, maybe ITAR or something, or your internet's terrible, or maybe you just don't have internet out in the shop, that's fine. Just go offline. The files aren't visible by Markforged or MLC CAD, but if it's ITAR, you can't put them on the cloud, and that's not our restriction. So there is an offline option available for the software to just run on premise in an air-gapped environment. We deal with that a lot. Another one is people talk about cloud being a money grab, right? It's a monetization strategy. You only put it on the cloud because you want to, suck us in or something like that. Well, Eiger's free. You can go right now and download, or I'm sorry, not download. It's on the cloud. You don't have to download it. You can go sign up and use Eiger right now. It's open. It's available to everybody. We don't allow open source third-party slicers because the temperature, the content of the wax in the materials, the slicing, there's so many different things that have to be tweaked just perfectly for this to work that it's simply not possible to have any support for third-party tools. Now, a lot of times people say, well, I'll just go, get my own metal filament and my own printer and make it. And that's possible. There are some resources out there for that, but I've found almost no success stories outside of research. And research usually involves a team of people working very hard, long hours, to get very little actual production done. It's not a profitable strategy. It's fantastic for, advancing research and technology, but it's not going to get the job done. So it's a closed environment, end-to-end, single source, for a reason, so that it can be suitable and reliable. With the cloud, though, there are some really nice benefits. Automatic updates come out down the line, and when I say updates, I don't mean fancier icons. I mean, they come out with a new algorithm to figure out how long to wash a part, and they figured out they can get away with cutting the margins a little bit, and they cut the wash time down in half for parts. Just reslice it, and you're ready to print a whole day faster, possibly, because of the advancements they made in their research labs. So those automatic updates and improvements come out, new capabilities such as new print layer heights, the ability to disable raft, the tracking, the organization and reporting of all your jobs. There's absolutely zero install required, and you can do it on any app, any phone, any computer, any operating system. As long as it's on a Chrome browser, you're good. And that offline option is available for anybody that needs it. So cloud is not an impediment. It is a benefit. We highly recommend the cloud version. It's fantastic. But if you need that offline option, it exists. Shrinkage is another one that a lot of people freak out about, and I totally understand. In fact, I had the exact same problem or concerns the first time I saw how this worked. I said, there's no way that this thing is going to work the way it does. It's got to kill the accuracy, right? Shrinks 20%. Well, actually, Eiger analyzes the geometry, and it tries to sort of reverse warp and reverse shrink the part to offset it so that when it shrinks, the final part is as near net as possible. In the video I said it was about 20% shrinkage. It's about 20% because it's controlled by an algorithm that may change based on shape. It's actually going to be a little bit different to try to give you the best possible output. If you're looking for kind of an estimate of where to expect accuracy to be, in a vacuum, brand new part, first time you run it through, you can expect an accuracy of within about 0.5%. So for a 1-inch part, you would expect the tolerance to be plus or minus 5 thousandths. Now, that does get better over time, and the repeatability is amazing. So if you print something and you find out that it is plus 2 thousandths, for example, the repeatability is going to be fantastic, and you're going to get that same output over and over and over again, which is a really amazing, side effect of this process. The surface is mill finish, so if we say, plus or minus a couple thousandths, that might be literally the surface finish to expect as well. So it's certainly a mill finish. If you need anything smooth, if you need a specific surface finish, you'll definitely need to go and clean that up with a CNC or with a grinder, sand it. I have sanded and cleaned up some surfaces. They look absolutely beautiful. Below that very top surface, it's a very solid, cohesive, metallic material part. A lot of times people will think, okay, well, sintering is going to ruin the shape. It's going to droop. It's going to drip, drab, whatever. The parts aren't melting. The metal crystals are simply allowed to grow, and the boundaries between those crystals is softened so that they can merge together. The material inside, if you're trying to think of it, kind of visualize it, it behaves like clay inside the part, almost like Play-Doh. So if you build a part with Play-Doh, you build a castle out of Play-Doh, as long as it's kind of short and fat, that thing ain't moving once you build it. But if you make a really tall tower, it might fall over, and that's exactly what would happen in the oven. So make parts stable, right? Don't make them tiny, tall, unsupported columns. Don't make big overhangs. But as long as it can be made out of Play-Doh, you're probably totally good to go with sintering in the oven, and it's going to give you an extremely consistent result. And there's a full design guide available that's fantastic for helping you to kind of come up with ways to design your parts that are optimized for the Metal X printing. Not only does it help you to kind of streamline it and make it work faster for washing and be more repeatable for sintering, it also gives you information about how to heat treat the part when it's done, sizing features for minimum use, all that kind of great stuff. Now, speaking of accuracy, there's something coming down the line called blacksmith. I mentioned there's an algorithm in the background calculating the warpage and kind of reversing the warpage to print sort of the unwarped shape so that it warps down to the final shape that you want. With blacksmith, it closes the loop completely. What I mean by that is you would build your CAD part, you would build your geometry in the shape you wished it would be when it was done. from there, you'll print it, and Eiger will do its very best to make it as accurate as possible, but it's guessing. I mean, it's predicting where it thinks that part is going to be, and it's going to get you within plus or minus 0.5%. But you're going to be near nominal on your final part, which is great for most things. But if there's a part that requires a higher level of accuracy, you can then take a scanner and scan that part into Eiger, into Blacksmith, and it does a full deviation analysis. That deviation analysis then feeds back into the artificial intelligence algorithm, and it says, okay, well, with parts like this, I guess in the X and Y axis, it shrinks more or less than I expected. So I'll update my algorithm. The next time you slice that part, the print will be way more accurate because it improves the scaling factors across the entire part. And it's not just for that individual variant. Because it's using artificial intelligence, it's teaching the machines how to print the part more accurately. So even if you're not doing any scanning and feedback and teaching the AI, if anyone is doing anything near the shape of your part and scanning it and feeding it back in, it's going to feed the algorithm, which is going to improve everybody's accuracy. So right now, with this, in its current state without Blacksmith implemented, you're still going to get a good accuracy, but it's about to get a whole lot better. We also get a lot of questions about porosity and strength and purity, and basically just people saying, well, I don't believe that that part, that stainless steel, is actually stainless steel, right? Is the part porous? No, it's a 99% part density, over 99%. So that's going to be a lot similar to like a billet material. If you buy cold rolled or hot rolled steel, you're going to see a density in the high 99% density range. If you cast it, it might be lower. If you forge it, it might be higher. But you're in the same category as any other raw material that would be considered simply stainless steel. There's no asterisk required. Now, the parts can be porous in the sparse fill, which is kind of unique. So a lot of times people say, are they porous, thinking that's bad? But if you're looking to reduce weight, you can make them sparse fill, and they'll be a lot lighter. In fact, if I was to give you a typical Metal X part made of stainless steel, you'd have a hard time guessing based on its heft, based on its weight and how it feels in your hand, guessing what material it is. Because it would almost feel like the heft of aluminum rather than steel because of that lighter weight. Other things involve kind of secondary applications, right? Can I machine it? Can I weld it? Can I heat treat it? And the answer is, yeah, it's a metal part. These finished parts are metal parts. Just treat them like metal parts. Weld them, machine them, coat them. If it works with that material elsewhere, it works for that material here. Very, very simple in that respect. And I understand the skepticism, absolutely, but it works fantastic. Are the parts strong? Yes. Unlike the direct metal laser sintering and the welding, there is no Z effect. There is no local heat affected zone. The sintering process removes any Z-axis effects and any localized problems that would be caused by other traditional metal printing technologies. If you need it to be even stronger than a part with sparse fill, you can make it solid if you want to. Sparse fill makes it, use less material and makes it print and wash faster, but it is possible to make it completely solid. Now, the other thing about strength is a lot of times, let's say you're machining something out of a billet or out of a bar stock, you're limited by the constraints of the raw material. With bigger raw material, you make more waste, you make more chips, and so you want to keep the material as close to the final shape as possible, but then you usually end up with a weak area, kind of a part where you simply cannot make it any bigger in that area, and that's the area that's most likely to fail. Because you're not constrained by raw material shapes, grain directions of raw materials such as sheet metal, you can thicken and thin it down in very strategic ways to make parts that are much stronger without being excessively more expensive than other parts that are of the similar shape and size. So it's pretty amazing. If you're looking for parts that are extremely strong, this may actually beat out a lot of traditional manufacturing methods. Now, as for the materials themselves, what's available? Well, right now it's stainless steels, tool steels, Inconels. There is copper coming extremely soon, titanium. We do see more on the way, but right now we're seeing just a bunch of stainless and tool steel variants, which makes a lot of sense because Metal X is perfect for dies. Just about anything that you would normally build out of tool steel, you could print it out of tool steel quickly and easily and get an extremely strong, durable part without a lot of programming and tooling costs. Because tools, in general, the cost is as much in the handling and programming as it is in the material or anything else. So things that are also a little bit exotic or maybe harder to machine, like Inconel and copper, those tend to be ones we're seeing coming sooner rather than later. For heat treatment, the center one doesn't specifically do heat treatment, meaning we're not sort of using it as a sintering oven at the current time. There's no protocols to do that. After it's sintered, it's a little bit like an annealed part, near annealed for most materials, meaning you're not going to have any cold work, you're not going to have any residual stresses, and the material can be heat treated from there. That material design guide, or the Metal X design guide, has some fantastic heat treatment guidelines to kind of give you a formula for how to take from where it came off the oven to get it where you want it to be exactly for material properties. And then aluminum tends to be a big question people ask. Hey, wait a minute, what about aluminum, right? I'm finding that aluminum is extremely popular, but if you back up and ask why aluminum is extremely popular, because I agree, I love working with aluminum. Aluminum is not terribly expensive, it's not terribly dense, it's corrosion resistant, and it's easy to machine. Now, if you back it up and you say, well, instead of asking for aluminum, I'm asking for those capabilities specifically, then stainless steel actually becomes a much better option, especially with the sparse fill, because a lot of the cost in this material comes from kind of the powderization of the materials, the metals. And so by using stainless steel, you're not really going to spend more money, but you're going to get a great part with a similar strength-to-weight ratio, or even stronger than aluminum in strength to weight. And for other parts, a lot of times you're just looking for something stronger than plastic. Well, what about carbon fiber? You can actually print very quickly same-day parts that are as strong as aluminum, but even lighter than aluminum, out of a Markforged composite printer. So if aluminum is a deal breaker because it literally has to be an aluminum alloy, I understand, and that's not yet currently available on the Metal X. But a lot of times you can find a suitable, if not a superior replacement without really giving anything up. And as far as tungsten, a lot of those tungsten carbide materials, they would have to be sintered separately because the sinter oven does not get hot enough for those materials. And I don't see that on the horizon, but you never know. So that brings us to cost. People think the machine is too expensive, and I get that. But keep in mind, the Metal X is 5 times cheaper than any alternative metal printing process when it was released. I mean, talk about a breakthrough. How often do you see some technology drop in price by 5 times with the release of a new system? So it's in the $100,000 to $200,000 range to get going. So it's not for hobbyists yet, but it's not $1 million either. So if you have a legitimate ROI, this is a very plausible thing for you to get, and it's in line with a lot of other manufacturing equipment. The material is more expensive than raw material would be, but that's because it has to be powderized, bound, mixed, and everything else. It's got a very strict quality control. Any problems with the material or any problems in even just one spool can ruin a part. So the material is very high quality. It's a large part of what makes this system viable. And we don't support third-party materials, but I'm really amazed. I kind of expected Markforged to really kind of bend their customers over a barrel on materials because I figured that's how every company makes their money, right? They suck you in and then they make you buy their own consumables. But the material has been on par with other materials in this realm They're not going crazy on these materials. And so, given the process involved to make it, the material is in line with what you would expect it to be. And then a lot of times people say, well, that's great, but you can make this faster or cheaper on a CNC or by casting it. And I understand that, but this is not supposed to be a replacement for traditional manufacturing. And not all companies can benefit from a Metal X. And this slides directly into the ROI discussion, because cost is an important factor, and we do not buy these machines because they're fun. We buy them because they make us money, because we need them for our jobs to be able to be profitable and compete in the marketing of the landscape. So here's a couple terrible ideas just to kind of kick off the ROI discussion. Not to make fun of anybody who thought this, but basically one thing that some people sort of think of is, well, wait a minute, I can't just throw away my machines, my lathe, my mill, and my laser just because I bought a Metal X. And in fact, we don't want you to do that. Don't do that. Don't expect to do that. This is not a replacement for production. Do not expect this to replace normal production. This is not a high volume process, right? This is not going to be great if you've got a lot of things that need to be done over and over again. We'll talk about the quantity ROI in a minute. And don't expect this to be the number one thing you use to build your parts. In other words, don't just, a lot of times round parts, you put them on the lathe by default because that's what you do with all your parts. And you just assume any round part is going to be put on the lathe because that's where everything goes. Don't treat the Metal X like your lathe. Don't put every part on the Metal X just because it can be put on there, right? You really got to kind of think this through. Let's talk about what this looks like and what kind of parts you'd want to look for in order to decide whether the Metal X is for you. Because honestly, the Metal X is not for everybody. So if you're looking at kind of the complexity of your parts and your designs, you probably think is a fairly normal distribution in that you've got purchase parts that are so not complex. All you need is a part number and they show up, right? They're cheap and powerful and strong and precise. They're great. And as you kind of work up the line, you get parts that are more common that are fairly easy to manufacture, but then you start getting into parts with multiple operations and multiple setups and complex materials, undercuts, and you get to where you're in the point where the fabrication of that part is extremely difficult, if not downright impossible in some cases, to manufacture. And so you're paying an arm and a leg just to get that complex design built. That's where you use the Metal X. Don't come to the Metal X with simple parts that are cheap to do another way. If you have a solution for it, keep doing it that way. But if you've got a part that is difficult or impossible to machine or cast, and the geometry is so complex that you've got to go to extreme lengths just to get it made, if you're making lots of material removal where you're just removing tons and tons of material from this part and it doesn't fit a raw material shape, if there's complex interior details that make it extremely difficult to get in there with tooling, or if there's severe weight restrictions, that's perfect for the Metal X, because these parts are not going to be super cheap. But if you have a part that fits the category of difficult to impossible, suddenly the price per pound of a Metal X part is actually amazing, an absolutely beautiful thing. So if you don't make anything complex, this might not be the right thing for you at this time, because it's really a powerful tool for what it does. A lot of times I also see this being a real big benefit for people who don't do certain materials often. So if you need a special machine specifically to make copper or titanium or Inconel parts, instead of buying a brand new CNC for that, maybe get it as a metal printer instead, and you'll be able to not, your ROI is going to look terrible in both places, but by doing production on the Metal X, right, you're going to save money in the long run. So anytime you have something where you'd have to be constantly clearing out your chip conveyor to change over to another material, or you're using a material you're not typically using, such as stainless steel when you normally don't do any steel, that could be a really cool opportunity for Metal X. So a couple kind of red flags that say, hey, let's at least talk about this, would be a part that contains multiple setups and operations. If you're constantly turning the part and re-indexing it and clamping it to machine multiple different steps, that might be something to look at for the Metal X. If you've got parts that had to be built as 3 or 4 or 5 parts in an assembly because the part you really wanted couldn't be made, think about making it as a single part and printing it on the Metal X. And if you've got parts that are a high volume of expensive chips, right? You're taking 90% of the material away in chips. Suddenly, the cost that you're wasting on the chips to buy them and then try to recycle them is much better to just print it additively from metal powder. And anything that involves expensive or extensive tooling and fixturing, where it's going to take a ton of time, maybe the part's really organic, so you're going to have to make custom stuff, that's a scenario where the Metal X might really shine. Also, you can start to look at the life cycle of your parts or your products to look to see where you might be able to find use cases there. For example, in the prototype phase, the early development phase, those prototypes, if they don't work, you're not going to get a benefit of building the tooling and the programming by making it in the full production capacity, by making a prototype that doesn't pan out. Building early prototypes before the product is even ready to be released and tested is a really great way to do it. Also, these are full strength prototypes, so you'll be able to not make a bunch of compromises with plastic, cheap toy parts. These are full strength metal parts. So you can print them and then run them through, regulatory testing, or run them through any kind of cycle or design failure loads, and make sure it's going to work before you invest a ton of money that you'll never see an ROI on. Tooling is another big one. So as a part gets done and you say, that's great, I need to build it now, but I need tooling. I need end-of-arm fixturing. I need jaws. I need something to hold this thing together while it's welded or whatever. This is another great place where you really only need one of them. And so printing it on a printer beats out the cost of tooling up and programming out the part and buying the raw material. And then sustainment, I think, is another one that a lot of times people might overlook. And what I mean by that is, let's imagine you've been making a part for 30 years, 50 years, 100 years. You've been making this machine, and obviously you've been making improvements over time, and you've got some customers that buy tons and tons of your product and have for years. And they call up and they say, hey, we need this part built, and you need to deliver it to us because we are one of your biggest customers of new and old machines. Well, if you've lost your tooling, if you've lost the equipment that you used to make it, right? Things get lost to time. The ability to build almost anything out of metal for relatively low cost is a really powerful capability for keeping those customers happy in a legacy situation. Most of the time people think about the parts that make them money, their growth and mature parts, where you're making tons and tons of them, and that makes perfect sense. It's on the top of your mind. It's where your money is made. But Metal X is not necessarily going to be there to enable your daily operation. Now, what it can do is it can free up your CNC machines. Those are the ones that are doing the bread and butter part production. This can free them up from one-off prototyping and tooling. But if you have a part that's mature and you're thinking about how you might use the Metal X, look for areas where maybe you're redesigning it for service failures, because we've seen a lot of customers build parts that were previously impossible to fabricate. They're now printing them as single pieces, and they become extremely durable because it's a solid, cohesive piece of metal rather than an assembled group of pieces. If you're looking to value engineer or diversify, right? Take your part and you say, well, we want to use it in this new application. You could print out the necessary add-on pieces to take it and adapt it to a new, new application or a new industry without having to tool up extensively to try out that new application. So there are tons of places where you'll use it, but it's not in that day-to-day full-scale production. Part quantity is just exactly like one of the number one things that determines whether or not there's a possibility for an ROI for a Metal X additive manufacturing. With traditional manufacturing, you have to spend time kind of setting up the production, setting up the tooling, programming the CNC, or whatever it is. Even just finding a supplier for the raw material and getting it in-house and getting it cut to the right size. There's a lot of stuff to figure out, but it pales in comparison to the cost savings once you get into full production and you create a bunch of quantity. Additive manufacturing does not scale very well, meaning past about 100 parts, you're probably not going to see any benefit from additive manufacturing for most situations. So if you don't need more than 100 parts of something, consider additive manufacturing. If you need more than 100 or near 100, you're probably not going to do that on an additive manufacturing system. But if you've got parts that you only need 1, 2, or 3 of, we typically see customers report back 50% cost savings on making their parts in this way, simply because of all the steps that are required to get it into the shop. And that's not even counting the reduction in disruption to production. In other words, I'm not going out there pulling my best machinist off the line to have him tool something up. He is going to just keep working on production, and I can build these things out separately myself. Custom equipment manufacturers. This is a CNC manufacturing cell I built early in my career, and it was completely custom. It's one-of-a-kind machine. And the main restriction in this entire system was rapid delivery. And yet we had these steel parts that we had to get fabricated that ended up taking a very long time to get, to ship, and everything else. It seemed like the entire system was the integration of multiple off-the-shelf parts being attached and connected to where they would create the final part. Well, imagine if you could, instead of putting out for bids, sending it out, getting the part in, inspecting it, making sure it worked, what if you could just hit print, and a few days later your metal part is there ready to go and it's full production use? So for custom manufacturers, or even engineer to order, there's a tremendous opportunity here, because even if a part is 80% standard, you're still going to have those special requests. I need a sensor here, I need a door here, I need a bracket, a handle, I need something here for me only. Can you accommodate it? And instead of spending your time browsing through the McMaster car catalog, you can simply design the exact part you need and hit print. And this applies to both composite printers and metal printers. A couple additional things to keep in mind for the ROI. Think about places like Alaska or offshore facilities like oil rigs. You may not have the ability to just go down to the store and buy a screwdriver, or even worse, some piece of specialty tool or a part that breaks out of the blue. Right? If everything you do is expensive, suddenly the ability to print whatever you need on the fly, fully self-contained, is extremely valuable. Right? I mean, even just raw materials, maintaining a raw material inventory of bar stock, blocks, things like that, would be very prohibitive on a remote platform. And just being able to stock spools of material to be able to make anything you would need would be very compelling. Also, just the simple, not disrupting production anymore is huge, right? Being able to print and make parts quickly and easily that are full strength are really awesome. These parts are very heavily automated. In other words, you just say, I want this part, put it here on the printer, go. And the screen tells you what to do, and it just runs for a couple days, right? You don't have to babysit it. It'll email you if there's anything wrong. You can set it up to do fast turnaround one at a time, or you can do it for long unattended operations, so you can kind of ignore it for a week. It's way easier to train a Metal X operator than it is to train a CNC machinist. Those are not equivalent in terms of skill sets, knowledge and background, and the ability to create usable parts based on an introductory knowledge of how to do that job. Cost of ownership is pretty low. I was actually really surprised at how low it is. If you need details on this, let me know. But consumables are pretty low cost, especially when you consider comparing this to things like CNC tooling and fixturing and everything else. And a lot of the consumables, things like the print heads and whatnot, are included in the customer success plan. So you may be surprised at how low it is, the cost of ownership, to keep this machine running, even in full non-stop production. It's really not too bad. The main thing is going to be that material cost and the time. And there's absolutely no surprises there, because it's constantly telling you how much it's going to take in terms of time and in cost. So the prices are very well known. They're very well understood, and there's not a lot of gotchas. And if you want to scale this up, it's not like a CNC where you need to basically double the floor space, buy another machine, get another machinist, or add another shift, right? You can actually scale it up in kind of efficient ways. In other words, buy one more printer, but then you can still use one wash to service both printers. And then you can still use one oven, or you can have a couple of ovens and kind of build a print farm. There's print farm software built in, ready to go to service your needs the most efficient way possible. And it's kind of a really cool system that way. I hope that this has been useful. I hope that this was interesting to watch. I find the Metal X to be an extremely cool thing to use. Reach out to us anytime and let us know if there's anything we can do to help you, or to see if Markforged Metal X is right for you. Thank you all very much for attending. Have a great day.